in section 6.4, we get introduced to a topic that I think you will be very happy about. Let's go back to the very beginning of chapter 6 when I introduced the concept of truss, and we looked at a problem that had a bridge in it. It was something like this. I think you all should probably remember this, where I said each little triangle was 6 wide, the bridge was 4 tall, and we had a load here of something like 20 kip, and then another load over here that's something like 5 kip. And we solved for the reactions here. I want to say, going off of memory here, I think this one was like 14.2, and this one was something like 10.8, I think. These numbers aren't super important, but I think they're pretty close. Okay, you can go back and look in your notes to get the exact numbers. And from this point, what we had to do is we started, say we wanted to know the load in this member here that I've circled. In order to find that, what we would do is we would start maybe here, and we would write 2 equations for equilibrium so that we could find the load. If we labeled this A, B, C, D, E, F, and G, we'd start and maybe we'd find the load in AB and then the load in AC. And that would allow us to go up to B, and we could do the joint B, so we'd find the load in BC and BD. And we could come down to C because we'd know AC and BC, and we could work our way through, right? So we'd have a ton of equations to get all the way to the point where we could solve for DE. The good news is there's a better way to do this, and it relies on the fact that this guy is in static equilibrium. Okay? So we're saying, look, the bridge is in static equilibrium. Not only is every piece in the bridge in static equilibrium, but the whole bridge itself. And so if I were to do something like cut the bridge right here and expose the forces that I cut, it should stay in static equilibrium. What do I mean? What I mean is that I could redraw the bridge. Sorry, I could redraw the bridge. Here's my one triangle. Here's my cut. Here's another piece of the cut, and here's a third piece of the cut, okay? And this is G, F, and E. And I know that I have 10.8 kip acting down here, and I have 5 kip acting down here. And what I've done is I've exposed 3 loads. I've exposed what I'm going to call F, FD, and I've exposed FED, right? That's the one we were interested in. And I've exposed FEC, right? Now, if this is in static equilibrium, that means that the sum of the forces, well, let's just say the sum of the forces in general has to be equal to 0, as well as the sum of the moments about some point has to be equal to 0. So this allows me to now write 3 equations. So I can say that the sum of the forces in the x direction has to be equal to 0. And in this case, let's see what forces we have going in the x. If I'm going to say to the right is positive, it looks like I have negative F, FD, negative F, EC, right? Those are the 2 horizontal ones. And then I'm going to have some component of FED, or the horizontal component of FED here, and it's going to be negative as well. And that horizontal component would be negative 3/5 FED equals 0. And that's just going back to our geometry, right? Because remember in the problem, if this is 6, that makes this 3. If the height is 4, that makes this 5. So the horizontal component of each one would be 3/5, and the vertical component would be 4/5. Okay? So what I have down here is an equation with 3 unknowns. So let's write another equation then. Sum of the forces in the y has to be equal to 0. Okay? Looks like I have 10.8 up. Right? That was the reaction at G. I have 5 kip down. And I have the vertical component of FED. So that'd be positive. The vertical component is 4/5 FED, and that would be equal to 0. Okay, so let's simplify this a little bit. That's 5.8 is equal to negative 4/5 FED. Okay, and I think we could eventually solve this for FED. I want to say it's like 7 point something. I can't remember exactly, 7.7-ish kip. Then the third equation we can write would be that the sum of the moments about a point, and we can choose any point that we want. I'm going to choose point E. And the reason I'm going to choose point E is because it eliminates this kind of crazy FED, and it eliminates FEC. All right, so I'm going to sum the moments about point E and set them equal to 0. Counterclockwise is positive. Summing about point E, then I'll have 10.8 times 6, right? Because these are 6 wide up here. I guess I'm off the page a little bit. These are 6 wide. So it's 10.8 times 6. I'll have minus 5 times 3, right? Because 5 happens right in the middle. If this is 6, then that would mean it's 3. And then lastly, I'll have plus FD times 4, the height. And all of that has to be equal to 0. Okay, so let's see, 10.8 times 6, that'd be 66 minus 4.8. I think it's 62.2 or so, 61.2. Minus 15 is equal to negative 4 F sub D. Okay, so you can see with these three equations, I'll leave the going through and actually solving for the exact numbers to you because I don't have my calculator handy. But with these three equations, we can go ahead and solve directly for the load in member DE. In the method of joints, we would have had to bounce at joint A to B to C to D to get that, or start at G and go G, F, E to get it. So 2 equations, 4 equations, 6 equations, and here we can do it in just 3. Now the trick to the method of sections is you can only cut, and I'm going to put that in parentheses because we're just kind of theoretically cutting. You can only cut a total of 3 members in order for this to work. So I could not go ahead and I just need to be very careful about where I cut such that I only expose 3 members. If I expose more than 3, it's not going to work, right? So only cut a total of 3 members. First, solve for reactions. And you have to always include loads applied to the piece you're analyzing. Okay, so what I mean by this is when I cut through here on the diagonal and I redrew this, I still had to put in the 10.8 kip reaction that I figured for the whole thing, and I also needed to put in the 5 kip load that acted straight down because those are acting on this and need to be accounted for in these exposed forces. As usual, anytime you expose the force, go ahead and draw it as if it's in tension so the arrow comes out of the cut. And that'll be a good practice because then if you get a negative answer, you realize it should be in compression. All right, method of sections is more direct when you need just a single load and you can cut in a way that only exposes 3 loads. Method of joints is more direct when you need a bunch of different loads throughout the truss.